Welcome back to our second part of Practical Lecture 5.1, Understanding MPI Communicators and Data Structures. So in the first part of our Practical Lecture 5.1, we had non-blocking communication examples, very trivial ones like I send and I receive, which are non-blocking operations, essentially requiring some form of a wait. And there are two types, essentially. You have seen we can have a wait with a specific MPI request linked to one of those non-blocking operations, but we have also ideas of how we can do this with, let's say, an MPI wait all, and then essentially have this combined in a lots of different requests that we had essentially seen in this Cartesian communicator. And the idea of the lecture was really to understand this Cartesian communicators better. And of course, our assignment 2 will be all about it so that you really have a hands-on by yourself to really understand that fully and to do shifts on your own. While you always should remember, this could be an exam question, that the shift is actually not really doing a shift. It is just preparing the shift by filling essentially the necessary source and destinations of the neighborhood processors. That's quite important. We have seen also the number of processors should be matching the dimensions of the Cartesian grid. It's also essential we get the Cartesian coordinates nicely, which are not directly the ranks anymore. It's like your identity in the Cartesian grid, depending on which row, which column you are. And then we have seen that, of course, you can combine these things which we learned, which means we have the non-blocking operations that you can then bring in essentially into the Cartesian 2D grid that we had in our ocean idea, starting really with a foundation for your assignment to how to program such an ocean by having all these tiles. And by all of these Cartesian communicator examples, you have seen the important key message to take away is really, this is 12 times executed. This is 16 times executed, right? These different examples is basically a key to understand that, of course, we have a parallel program, right? Which means every processor involved running this. But the beauty is that the MPI environment then gives us the different identities, not only with the ranks, but of course, and also with the Cartesian structure. Then when I create this communicator from MPI Com World, then and basically have a very nice way of having a systematic message exchanges. We did one example where, let's say, we communicate with all our neighbors. That has, of course, it's not a requirement to do so, but it shows a nice example what happens if you have 4 neighbors, to send something to all your 4 neighbors and also receive something from all your 4 neighbors. For this to happen, we need a periodic setup, you can imagine, because otherwise sometimes we will leave the ocean for those ranks which are on the boundaries. And with this, the periodic behavior is, of course, very important. Now, the second part of the lecture now is going a little bit into a different direction. So essentially thinking more about data structures again. Of course, it's related to communication. It's related to your kind of domain setup and your domain decomposition, as we have learned in lecture 5. But here we want to look a little bit more into the data structures and not put an emphasis so much on the message exchange itself, but rather what can we do to really have, let's say, more complex data structures supported by MPI. And we will do some motivation why we need to do so. Then on the other hand, we also want to think about what about a large scale problem when I have a large number of particles, or when I have a, let's say, clustering algorithm with lots of data points somewhere, we call that a point cloud. And I want to cluster them together in order to reconstruct, for instance, the Bremen inner city that was laser scanned as per cloud point as one example. And there we use really elaborate data structures called parallel IO and basically parallel file formats like netcdf, but also HDF5 that we have as an example here in the second part of the lecture with really practical examples so that you can get a better idea what it's really about. So let's start a little bit again by the communication overhead. We learned by the geometric decomposition the last time when I chop down my area, perhaps, let's say, too large, then I have little parallelism, right? And the computing is still very intense for all the big tiles here. However, on the other end of the scale, if I want to do it too much and make it too small, then in order to, let's say, compute the weather, for instance, if you want, or the wind across basically here, this kind of country, then we basically have lots of communication and exchanges between them. And if it's too small, then basically the communication is quite intensive, while the compute in each of these different tiles is basically very small, and perhaps sometimes even idle, just waiting for all the communication exchanges to happen. So it's a not trivial issue to think about this communication overhead in terms of your decomposition. Indirectly related essentially is also the idea now what I will come to with the derived data structures, because now if you think about that you want to have different chemical ideas, chemical variables that needs to be exchanged between all the tiles, right? Not only wind speed, maybe also other parts, aerosols through the particles, whatever it is, maybe ash cloud, aerosols, and so on, which are really, let's say, domain-specific elements. And you want to have lots of them transferred. You always start with send and receive, or basically have lots of these mini messages, so to speak, coming over the wire. So the question would be, what about more arrays that I want to put over the wire? Or what is when what would happen if I have 3 times an integer I want to have, communicated to my neighbor? Do I really need to do 3 times send and receive in a for loop, essentially? And here the answer is no. We have exactly for this the MPI derived data types. Of course, we have also, let's say, on the basic type, we have the typical MPI data types, which are really the basic data types. You see here examples. We have MPI int, MPI chars, MPI floats, essentially representing what we already know from typical C, but also being prepared already for the MPI environment. And essentially, the little bit of difference is when you think about MPI, you always have to think about memory locations. That's why we will come to this also when we think about the 3 examples of the derived vector and also derived indexed ones, where you have to think about more about the memory location inside your processors. And I will make a point to it when we have these examples. But essentially what we used here was always an MPI send and an MPI receive operation. And I say how many of those, I really want to put over the wire. So I have an integer counting how many of those. And the MPI data type was always, let's say, one of these simple types so far. Now the question is, what would happen if I would have multidimensional data sets? And for our examples, we will keep it simple. We do a 2D setup, maybe starting first with 1D setup, saying just 2 integers, but then we really move towards kind of a column vector I maybe want to transfer out of a matrix, or then maybe a triangle of a matrix. So how that would work? Do I really have to send them all of these different values from this matrix again and again in simple messages? Or can I combine them to a much smarter data type, right? That's where we're alluding to in order to really save the communication overhead all the time. I just do it once. In order to do so, the derived MPI data types, there's some principles. We construct them. Firstly, using a couple of dedicated MPI routines, which I will talk about exactly in my basically examples. We already talked about them a little bit in lecture 5. Which were contiguous or vector and indexed. And there are also other ones that I didn't talk about and I don't really present, like struct and so on. But let's say if you understood the first 3, then probably you can also work with the others. The important thing is you have to commit this data type then to the MPI environment. So basically with this MPI type commit operation you see here, that is kind of a key ingredient, because otherwise MPI doesn't know about this data type. And you can imagine when I have a send operation and a receive operation done by different processors, we have to have this type commit to really see that all of the processors know this data type. And then you can really use this data type and say, even, if you want to have it once or twice or 3 times over the wire, so to speak, to the next processors, as you would do in a normal send receive as normal basic MPI types. Just instead, I use this derived MPI data types, which are much more advanced structures, as we will see in a moment. In a way, how I do this and what I will do with this is I avoid really this repeated sendings, right? Which is really a bit slow, it's clumsy, it could be also error prone. And with this, I have really a good suitable memory layout of really extremely complex structures that could be not only all of MPI int, so it could be also, let's say, MPI int combined with MPI float. So there could be also different data types combined in one when you have this kind of new, interesting derived data type. But this is so far for the theory. Let's come to a really practical example, and then you would know and understand it very quickly, I guess. So this is the first one. You have here the source code, and the top right, you see already what happens when we execute it. So let me demonstrate that also when we go again to our Uton environment. That's where we left in the Cartesian world. So let's go and have a little bit of look what we have here. We start here basically with the derived contiguous version. So let's see what that is, the derived contiguous, see what we do there. So essentially you see here a typical MPI implementation, MPI init and so forth, and the MPI com rank and so on. But what you also see is now exactly that we want to have something we call here a double int. Right, and it's a double int type. So it's an MPI data type that I just here initialize in terms of saying it's a type contiguous two of the MPI int basic types. So instead of using now one integer, I can always use two integers with the same, basically here, interesting double int type. I commit this, as you remember from the slides, to the MPI environment. And now I would say I have a different idea of what my rank is, sender and receiver. It's a different way how you can actually differentiate between those, a bit more for readability, but essentially reproducing what we had with rank 0 and rank 1. But here you see that the sender, for instance, uses just basically initialized here the buffer, really arbitrary numbers, 1, 2, 3, 4, 5, and 6, 7, 8, 9, 0. Essentially saying two integers that I now have in my buffer. And essentially I would here pick those buffer items specifically in my print. But what I meant with the memory layout is that you actually don't have to specify this in the MPI send itself. There you say essentially just the kind of here the buffer. But by doing so, you just specify you will send one from the double int type. And the memory location will make sure that it's basically fitting then essentially what you have done and committed here. So essentially there should be two MPI int types lying as part of the buffer set. And we have essentially those. And that's what we send over the wire without ever specifying that there are two, because we learned the two are combined in one. In the double int type. So I sent only one of the double int type and actually at the location here from the buffer send. You have the matching role, as you can imagine, from the receiver. So here we would say we will basically have received two items, right? So, so the size needs to be 2 because we want to receive two different values. And essentially here, I would basically say then that this is also a double int type that I have here in my MPI receive. So also here you see, I don't really receive 2, I receive 1, but I receive 1 from the double int type. So including 2, of course, right? 2 different versions, which is quite interesting. So now when you think about then what that means in terms of the output here, you have the rank, you have the received that you can have, essentially filling then the things which we have get here from this buffer of the memory location and filling it then with a double or with these 2 integers that are coming. It's a relatively easy code, essentially again a send and receive, so we can expect that this is something where we guess that you can, let's say we want to submit it, of course. Let's look shortly in the submit script as well. No surprises here, we just use 2, we call it the derived contiguous, and executing this particular executable we have here. I skipped the compiling. In terms of QStat, this is probably already finished. And we're looking for a job ID, which is the 47 at the end. So let's look at this. And indeed, there's a 47 at the end for a slurm output here. And you see exactly what we programmed in the C program. So we have the sender process, which is again rank 0. It senses values that was initialized in the buffer, and also the other matching receiver actually gets then these in his buffer. Although we just sent once, over the wire, we sent 2 values as part of this double int. And this is essentially now making it simpler. Instead of having, let's say, a for loop of saying send, receive 1, 2, 3, 4, 5, and in the next for loop 6, 7, 8, 9, 0, you have this all-in-one send operation and of course matching receive operation, instead of doing, let's say, for loops with many send and receives. I guess so far very easy, trivial, what most of you think. It's the same what I have here in the slides, more or less. Contiguous, think about the contiguous memory setup, right? So this is an important part of it. Here are 3 of the contiguous memory type. And essentially here you see what we just executed again, and here the source code. But let's look on a bit more interesting example, also to understand a bit more what it means with the memory layout when we talk about, for instance, the MPI type vector. So here what we want to do is we basically have, let's say, a complete domain. We actually simulate. You see here is a simulation domain or full array, which has interesting values we want to pick out, but we're not interested in the full array. We just want to communicate this column vector here, right? So what we really want to send is this. So how you would do this specifically without, every time defining now and picking those values explicitly. So this is now the interesting thing, how you could use an MPI type vector. And the interesting thing is that this then needs to be matching to what you have basically in your memory setup. Now, if you think about, and you have this array, how it looks in your memory setup, you would basically have this all in, one long setup here. And, you have a block length where the start of the block is, and then also the distance between the different blocks. And this is something we call also stride, right? So this is something what you have to basically say. You say how many of those you want. You basically say how long is one of these blocks you want to send. You see here, let's say we want to send 5, 1, 2, 3, 4, 5. Each of these blocks is actually 2, and the, let's say, stride, that's why there's always a blank in between. The stride is 3 here, in order to say where's the next start of the block. Now, when we now have this example here on the right-hand side, let's see how that looks like. We see here the buffer 3 times 3 is clearly this matrix, initialized with 0 up till 8. So they are not surprises. But as I said, we are not interested in sending this complete. We just want to pick out, let's say, 1, 4, and 7 here, the column vector, right? It would be 1, 4, 7. When I do this explicitly, you see how that would look like here in the MPI print. I would put buffer 0, 1, 1, 1, and 2, 1, right? Essentially reproducing here the idea of how it would look like in the matrix. But in order to avoid this, essentially, and saying instead of this, I want to have, let's say, a much more interesting data type for that, what I call a column type. And essentially saying the column type should be filled by integers. That's what we have here. And we say there should be 3 integers that are all, let's say, in one block. So 1 block length, 3 of them. But the interesting thing is when you now look how it essentially is here put on the array, then you basically need here a stride of 3 in order to say what is the start of the new block in order to send, right? And this is then saying when I have a block 1 and essentially I send this, then I combine it with a stride 3, again 1 block, and stride 3, again 1 block. And 3 of them I do, and with this I already have my 1, 4, and 7 I require. And this is essentially, again, an interesting part of it, because you see here in the MPI send operation, which I then using this interested committed column type vector, I don't specify any of this, right? Well, what I do is I give a pointer to the first, and because the MPI type vector is defined in that way, I already can then say, okay, this will be automatically filled by these things I explicitly put here in the printf statement. I don't even have to do this here. I just point to the beginning. And because I have one type of column type, it will automatically set, it's block length 1. Then I do a stride of 3, skipping over the values of these, coming to 4, skipping with 1 to 3, again over the values back to 7. And this is, of course, very interesting. Works also on the receiver side. As you can imagine, we want to receive 3 values. I mean, there's, of course, a very clear point in this. So that's what I have to create in terms of a buffer at the receiving side. And when I do this in the receive operation, I have the same situation again, that I just say I will receive 3 integers, essentially, that will come to me. And then essentially I can fill this array. So it also shows you that essentially this one here is using this interesting column type, right, to put out of the array this. But while here on the other side, basically on the receiver, I just don't need necessarily this advanced data type, because I could also work here in this example with a normal data type if I know, of course, that there will be this interesting structure coming over the wire. Now, this is an interesting example. Let's see when we do it in practice again. This time we have a derived, not contiguous sector, but more a vector setup. Could be interesting, as we've seen with the array. We go shortly into the source code, although I already was alluding to this. So it's essentially the same I just presented to you. So let's go out, look a little bit to the JavaScript that we have here. And also here, no surprises. I use 2 processors to really work on this. And essentially we'll just SBatch it and submit it. Shortly, QStat should be quickly done. We see here we require probably a 48 output, and the 48 output is also already there. We can look at it with more. And we see again, like basically without explicitly picking 1, 4, and 7, basically we send 1, 4, 7 over the wire. Of course, while this in the output, you remember, is really explicitly put here for process 0, for process 1, for process 1, it was not the case. Right here we received 1, 4, 7 as clear integers. And in the MPI process 0, we picked them in a column vector style out of the matrix and defining our own style. So then when we want to have another column vector picked, we just put another buffer as a start vector or start position in the memory layout, and will automatically pick again the layout of the column vector, which gives you the advantage when you basically now want to do, let's say, a setup and working with this data. Okay, so far so good. I think this is becoming more and more clear now. And I think these graphics, if you don't really understand it fully yet, think again about this graphic. This is this matrix here, more or less put in one long vector here, how it is essentially in memory layout. Then essentially what you want to have is just this setup. This setup you achieve, it's saying you always want to have 1 count, so 1 integer here, but essentially, I mean, you want to have 3 integers counts, yeah, so that is the count 3. You want to have the block length 1, and then the stride shows you when the next block starts, which is of course dependent on your matrix. In a 4x4 matrix, this would look different. Now, the next type I want to show you is the indexed one. It's of course a bit more elaborate. Of course, here also there's an interesting aspect that we have a full array. You see here we're creating this again like we have done before with a buffer 3 times 3, 0 to 8. But this time we want to send more or less a triangle. For some mathematical operation, this could be quite interesting to have just a triangle of the matrix basically sent somewhere to another processor. So what we do here is now thinking a bit more on displacements. So this is best explained again in this interesting graphic here. You have again the full array. We would say how many we want to actually send over, which is of course still for us now 3, right? We want to have 3 of them sent when we think about these aspects. And then we basically have different length that we want to send, right? If you remember in the triangle, we need 1, 2, and 3 from the type length. The original type remains, of course, an MPI integer, right? So the basic type is still the same, but the triangle type should be then 3 of them with the length, which is varying between the different ones. First, I send 1, then I send 2, and then I send 3 as part of the length here with the triangle. And this shows you also that you have to basically then think about the displacement. So from where I should start this 1, 2, 3, and with 0, you can see, okay, this is where we start our 1. With the displacement 3, that's where we start our length of 2 sendings. And then with the displacement 6, you essentially say you send 3 of the wire. More accurately, you see that essentially shown here, right? We have a pointer here, we send 1, but then we do a displacement of 3 and send 2. And basically we have a displacement of 6 and send 3. This is already much more complicated type. However, I think more or less with the graphic that is a light send here, it's really more easier to understood. Again, you can imagine the same principles go here. You see in the printf statement, we really pick explicitly here, very cumbersome, if you want, or clumsy, maybe all of those 0, 0, buffer 1, 0, buffer 1, 1, buffer 2, 1, and so forth. So this is, let's say, explicitly. I do this manually. But here you see when I send it in the buffer, I just point to the buffer and say it's one of the triangle type. So that means for my memory layout, I expect exactly what I defined here to find in my displacements. And that this works, we can basically show by having this buffer here used in our practical example, which also shows that on the receiver side, I don't care about this triangle type. All I care is that I want to receive this different 6 integers. And you see, I actually receive them here. And then in the printf, I actually give them out. So let's see when we execute this, what will happen. In this practical example, we do the derived indexed version now. Shortly again, going to the source code, just to prove that we do the same thing that you have here in the slides. You know, we have the different lengths at the different displacements. We say it's all from MPI int and define it as a so-called triangle type, right? And we commit it. And then out of the buffer that I have, and you know, here I put the outcomes really explicitly, I would just point to this buffer, which I defined is from one of the triangle type. And with this, I automatically got the lengths and displacements and know there should be 3 times these attempts with this different, let's say, lengths and displacements. And I do this, send it over the wire, and have, of course, the matching receive operation that I already was describing, just receiving 6 MPI integer basic types. So going to the submit, also here, no surprises. 2 processes will be executing this. So let's sbatch this, submit derived integer, qstat. Okay, it's already finished. So we're looking for a job ID, which is 49. And our outputs, not yet there. Ah, there it is. And see what's inside. And of course here, again, if you remember what we said was in MPI process 0, I really explicitly mark this 0, 3, 4, and 6, 7, 8. But you remember what I didn't do in MPI process 1, I really didn't do it explicitly. I really received it just at 6 integers in my buffer or my receiving buffer, and there it is. So the whole matrix is irrelevant because I picked the lengths and displacements as defined, and I have, let's say, 3 time attempts. And the beauty again is, like we have seen in the example before with the vector, this is all just one message exchange, right? It's one send and matching receive operation. Instead of now doing, let's say, a for loop, sending 6 times integers over the wire in different send and receive operations, this is all encapsulated in one send and receive operation of the triangle type, which makes it quite convenient. It's better for readability of the code, it's better for debugging of the code. And of course, you can keep the data structures together, because often you have matrices when you are basically in scientific codes, things we will see also when we have the second part of our lectures, then essentially in our second part of our courses and the lectures then which really start with domain-specific elements. So much for the derived data types. You have seen it's quite powerful in a way. You can really define interesting structures, but there's even something more powerful if you want, where many of these domain-specific applications we will come in the second part of our lecture will be using these. And this is the parallel I/O, the parallel file formats. There are different attempts how you use it. It's quite some flexibility. You can use them and reuse them for different, let's say, domain-specific applications. Here's one example, as I was also describing already in one of the lectures, the clustering algorithm. We will come back to also in lecture 10. So no worries if you don't understand the clustering itself. Essentially saying you have a point cloud, and basically those which have, let's say, specific minimum number of points in the epsilon neighborhood should be clustered together at the point, and then you have a kind of recursive way of connecting those clusters or identifying noise which have no points in the absolute neighborhood. And we talk about this algorithm more here. Today, we will just want to understand the data setup, the data structure. And then we come in lecture 10 much more to the algorithmic aspect of it. We have 2 different types of data set. We have the Bremen small data and the big data set. In H5, which is usually the ending when it should indicate that we have a, let's say, HDF5 system. And we run it then on one of these data sets, usually. Now, this indicates then that we want to basically have data somewhere inside essentially this kind of algorithm. And the beauty on this parallel I/O is if you have a parallel file system, it loads all of those cores automatically in parallel with the data. And this makes, of course, this parallel I/O format very, very suitable for parallel programming. At the same time, you have to think about all of these parallel processors when they do, let's say, the HPDBSCAN here, do their clustering. You have seen it created this interesting hypergrid first, then essentially clustering on this different hypergrid with the DBSCAN algorithm idea in order to form those clusters, doing it locally and then exchanging essentially here across the different splits and across the different here halos, then to make the final clustering labeling. But in the end, you still have all the data inside, some file. And this is something, of course, now what we have to think about, how that looks like when we, for instance, think about our Bremen inner city here. There was a laser scan car hopping here, let's say going one to one and one another destination and scanning, let's say 360 degrees around, and then creating, let's say with this laser scans, then always this kind of point clouds. Now, when you don't cluster them, it looks like a very arbitrary set of points. And with this, not really recognizable directly as a city. So we have to reconstruct the buildings by doing this clustering and then use some smart coloring here and there to really show then that this is essentially reproduced in the city of Bremen. So coming back then to this HDF5 format, how we would do this. We firstly have to have a library for this, which is HDF5. And then we have in here the idea of HDF5 to think about, essentially it's a file system. So we could have clusters, we could have the data itself, so the data points. We maybe have colors indicating where we want to have which color. So these could be different parts of those file systems I have here, most notably the point cloud, right? So I can define my own data structure here, a little bit as you have seen from the MPI derived data types, more or less saying slash this, slash cluster is that, slash data is this. So here you see you can even put different parts of it, arrays, tables, and all sorts of elements inside the HDF5 file. And that is essentially what we did here for this Bremen and Bremen small data set, basically in this particular setup. So let's work a little bit. Let's play a little bit with it. There are different aspects to it we have to understand first when you think about HDF. So let's go to HPDBSCAN. We have here prepared. And see a little bit what we have in terms of Bremen small. Now, I said to you, it's a binary file format, which means when I do now more Bremen, you would expect that this is not going to work because it's not a basically text file. It's a binary file format, so I don't see anything, as you can see. Not really fruitful to do so. And of course, what I now present here is also essentially captured in one way or another in the slides here. You have a binary file format. That means we need specific tools to do so. One of them is this dump file, for instance, here, which we can use, for instance, to look inside this interesting set of clusters. Also, this is also something we have here. You see here with HDF5 dump-n, I can, for instance, look on the first file system. Let's say file system is not really true. It's a file system, so to speak, inside the HDF5. So there we can already understand a little bit about the structure I was alluding to. So we would say in the first level, we would have the colors, we would have the clusters, and essentially then what's the output then of this DBSCAN and the data. So the interesting thing is now when you think about the data set, that of course what we want to do essentially in this Bremen city is just saying, are you part of one cluster or are you noise, right? So this is something from the data structure very important to us to think about. So essentially what we want to do is with this data set, we just read from the data set, but we also write from the data, write to the data set back. So all the data points which we basically load should get a label assigned to which cluster they belong. Which means also when you do now a little bit, let's say more HDF5 dump elaborate commands, what we say when we think about the clusters, right? So this should be the output of the cluster when we say Hi5 dump. And then instead of doing the structure, we want to already look into some specific data that we had in the cluster setup from this Bremen small. Then you essentially would look, everything is 0. Hence, it's initialized, right? So this means no cluster is assigned yet to all of this data because we didn't run it yet. Hence, what we will do now is essentially batch this interesting submit script. So let's look into the submit script a little bit to understand it. Here you see, interestingly enough, we have GNU, but we also need to load another module. And this reflects a little bit what we learned already in assignment 1. This was one part of it, right? So indeed, when you want to have HDF5, you have to do the module load. We also know OpenMPI needs to be loaded. This is not a surprise, but also here we load essentially the module about HPDBSCAN to have access to this executable. Which is here. The HPDBSCAN is just called DBSCAN, and we have the location of the small data set, but also of the big data set. Here, for the sake of the time, I actually just do everything on the small data set, but we have also a HDF5 file on the big data set. Big and small is best recognized when you think on the file system, right? The Bremen small, the size is found essentially here, and here you have a bigger version. The structure itself is very similar. So of course, there's no big point in the differences, except there, of course, much more points that you have and can cluster. Now let's look what that looks like on QStat. When we look on our queue, where am I? It's running. So that means my clustering is still processing. And I would inspect at some point in time an output here in the 50. So let's see what happens already there. Here we see there's already some output, which is alluding to some of the ideas of how DBSCAN works. And we will look back in lecture 10 more on concrete examples here. In the sake of the time of this lecture, we really focus on the data structure, on the HDF5, and come back then in lecture 10 how this really works from the algorithmic perspective. So you see here it's still doing the local scans. It has created the dimensions, the cells, distributing the points, sorting them, all the idea that we essentially have a bit represented here in this slide. When, as you see, we do a sort and distribution, we spatially doing it, we do a cost estimation of the split. What I already was saying in terms of load imbalance, we have to work with this if the points are not equally distributed. Also what we learned already with the, I think, Mona Lisa in our last lecture. And then we actually execute it on a couple of number of cores that we have here specified also in the job script. Here it's just 4. Of course, here we can play a little bit with the speed up, what you will also encounter yourself. Right, so because we're going toward the end of the lecture, we let them cluster. We go back in a moment to see how that was filled, this file. Again, important takeaway message is here, HDF5 is used for read and write. So we want to understand if these clusters we have looked and where all zeros are actually finally also assigned to something. We have these different data sets, which we have there. And in lecture 10, we will look a little bit into the idea of using just MPI or even hybrid, which means combining MPI with OpenMP. But OpenMP is something which is not obvious to you. We'll see how that materializes when we have our next lecture, which is lecture 6 about OpenMP, the shared memory programming that you nicely can combine with distributed memory programming. You see more fine-tuning here, how you run it. Also, this is something what we will allude to when we come to the hybrid lecture and also then to lecture 10, what essentially this OMP number of threads means. Now, towards the end, let's look a little bit what we had before. We said when we look into this dump here inside, and it was not basically run yet, we have all data 0, essentially saying, of course, the clusters are basically 0. And when I execute this now, what we will expect is that we would have a situation that this file, although it's the same file, Bremen small h5, has been changed. It was read into essentially HPDBSCAN. It did all the clustering. It found 21 clusters here as an example, and then wrote the different cluster IDs inside these data points. So you see many of them will be probably noise, but some of them really will be clustered together, and they are basically then bigger than 0. And those which are considered noise are usually then basically getting a negative number that you see here. So this is the way how DBSCAN is programmed, right? And basically how DBSCAN is programmed in that way of saying minus values are then no clusters, are noise. This is something what we reflect in the data structure of HDF5. No one told us to do it this way. We can also say it would be maybe 0 as cluster IDs. Although we want to differentiate it from the specific initialization, if you remember, that's why we do much more minus here as one example, essentially. Right, so before we close, let's look if the practice really is following suit here. Essentially, our QStat should hopefully be completed. You see, basically it took like 2 minutes. And when we now look into this output file of our 50, there's much more happening. We see this 21 clusters we were talking about. This actually depends on some parameters I have not talked about you yet. And these are these interesting setups here, the minimum number of points and the epsilon neighborhood that you can, of course, steer. How big is the epsilon neighborhood? How many points you expect to be therein to be the minimal number of points to form a cluster. But these are things we will look into lecture 10 much more notably, and then to basically better understand it. But we also see now that we want to have this checked, not only that we have all these clusters in the output here, now we expect that actually our Bremen small file itself has changed, right? Because we want to know which of those points are now basically a cluster point or which of those are essentially just noise. So here I can do another HDF5 dump that we had done before. Basically here we do the same thing as we did before of saying -d, and then had our clusters, if you remember, is all 0. in the Bremen small file. And what now happened, because we have run it, we expect that this is not anymore the case. You see here, essentially when I stop here, there are lots of noise, and some of them are then having, let's say, positive IDs when you look through all of them, as I basically have here in the printout. Some of them are positive and then form really a cluster. Of course, it's, let's say, depending on the parameters, so you find more or less clusters. You see quite a lot of noise points and some of the cluster points. All right, so I think that's it for the practical lecture. Many of these things which you have basically just seen in my demonstration, you will do yourself, and we have the walkthrough of assignment 2. And with this, I really would like to close the second part of the lecture. I hope it was very useful to you, also towards your assignment 2 that you basically have to start now, basically learning really how to execute an MPI and data structures and all of that together, and to program also towards the ocean assignment. That's it for today. See you next week.